I've fallen Slinky for Physics 2211. Here we have the introduction and objectives. So first is why I chose this lab. As a kid, I used to always wonder why a Slinky fell the way it did. And by doing this lab, I can almost show to younger me kind of how it works, and it's just a cool way to visualize and understand why a Slinky falls the way it does. And our objectives here are to compare experimental and theoretical data with tracker versus a closed loop simulation to visualize the motion of a falling Slinky. And with this, we are going to prove how the bottom of the Slinky will not begin to fall until the top has reached it. So first we need to go over our fundamental principles. We have Newton's second law, which is F net equals mv over t, or F net equals dp over dt, which can be rewritten to get and derive velocity and position update formulas. The velocity update formula is v final equals v initial plus F net over m times delta t, and the position update formula is rf equals ri plus v times delta t. Also, we need to consider the Newton's first law and the law of conservation of momentum. Newton's first law states that an object at rest will remain at rest until an equal or opposite force acts upon it. And the momentum formula states that mv equals mv, or mv plus mv equals mv plus mv, showing how momentum is conserved throughout the system. This is important because when we're showing how the bottom of the Slinky doesn't move, it's because no force is acting upon it until the tension is released above it and a force pushes down upon it. So right here is our tracker video, in which we will be able to see the motion of the Slinky. Right here, we see how this displacement line is flat until about 5.57 seconds when the top of the Slinky reaches the bottom of the Slinky. So we'll let this play. And you can see how right now the bottom of the Slinky is not moving, even though the top is falling down. But right around here, we see the top of the Slinky hit the bottom of it, and thus the bottom begins to fall with the top. Which is due to Newton's first law, as stated earlier, because of how the top reaches the bottom, the tension above the Slinky is no longer equal to the force of gravity, and the force of gravity is then able to drag the bottom of the Slinky down. So here's that graph a bit closer up. You can see how our y displacement is 0 meters for until about 5.57 seconds, and then the bottom of the Slinky begins to fall. And this height is based off of the height of the YouTuber in the video, which is 1.75 meters. So it fell roughly is negative 0.5 meters in total. To simulate this, we have our glow script code, where we first inputted our system mass, which is 0.218, based off an Amazon Slinky I found online. Our initial conditions, which are 0.000 and 000 for the Slinky's position and velocity. We have our time, which is 0, and our delta t is 0.017, which is based off of when I was playing the video in slow motion and clicking my tracker, how much through the video it went every time I pressed the button, and inputted a tracker point. We have the magnitude acceleration, gravity or survey, which is 9.8. We have the unit vector for the positive y-axis, which is 0, 1, 0. And we have our proportionality constant, which came out to be 102. This is found by just running our simulation with trial and error until we get a graph that models the one that we had from our tracker data. So right here quick, just a little break. Hope everyone's semester's going good. Good luck with exams. You got this. So here is line 2 for our code. So first we have while t is less than 5.7. This is due to how earlier we saw how there was no y displacement until 5.7 seconds. And so this is modeling the displacement of the Slinky during that time when the bottom is not moving. So first we need to calculate net force, which is W is equal to the Slinky's mass times G times J hat in the negative y direction. And tension is the Slinky mass times G times J hat in the positive direction. And this explains why our Slinky doesn't move for the first 5.7 seconds. Since these forces are equal and opposite, there is no acceleration until that tension is gone. So the Slinky will not fall down, its wave will not act upon it until the tension is less than the weight. And so now we have to do the velocity, but since F net is going to be 0, everything just, the velocity is 0, and thus the position will not change because we're adding 0 to 0, the position an infinite number of times. And so we now need to advance the clock, and that runs this loop. Our second loop is up until the end of it. So after 5.57 seconds, up until 8.833 seconds, which is when the video ends, we have the weight is equal to the same as before, negative Slinky m times G times J hat. And we have our delta force, which is our magnitude of the velocity squared times the normal of the Slinky's velocity. And when we add these together, we were able to model the graph of the Slinky falling over time. And then we have to do the velocity position as earlier. And as a result, we produce this graph right here. So we see how it's going, and going. This is a bit off. I'm not sure why it's showing 5 here, but it should be over here. And then it just falls, falls, and falls. And as you can see here, we start at 0 displacement. It goes, and then once it hits that point where the top reaches the bottom, it just falls as a projectile until it reaches the ground. So conclusion is the bottom of the Slinky did match my model I created in glow script, and the bottom did not move until the top of the Slinky reached it. This match was predicted and shows conservation of momentum. The bottom Slinky has rest until an external force acts upon it at the top of the Slinky reaching it, which is because of how tension no longer equals the force due to gravity, allowing it to fall. Thank you so much and have a great day.